Okay, so we're going to use camming today to do a profile that's an unusual profile, not just a trapezoidal move or an S-curve move, but I don't know, it could be cycloidal or just linear, give it a few points, position and time, but just some random profile, um, not a standard profile. So, for example, we want to make a position over time move where we have a constant change in position over time, and then at this time we'll have a new position over time, and then at this time it'll turn around and come back, and then so from zero position make the move and come back to zero, but slow down, stop, start slow, and then go fast again to a stop. So in the beginning, you'll be at position 0. It's in units of millimeters, so that, so many counts per millimeter, of course, but, we'll just keep the numbers simple for the moment. And then the time, so at 0 time, be at 0 position, so start at 0. And then at this time, 55 milliseconds, you need to be at position 19, at 70 milliseconds, position 20, at 85 milliseconds, position 19, and then at this time, 140 milliseconds later, be at position 0. So we have position column and time column, and we're going to enter this into the camming. We'll make a cam table. So on the basic setup, we choose the camming mode, and you can see we're set up. This motor has 10,000 counts, and you get when you select the camming mode in the table here, you get the cam screen. So what we're going to do for the cam table is notice the numbers look very, very similar here. The slave, we're going to run the master as a clock, right? So we want the slave to be in the beginning at 0 milliseconds to be at 0, at 55 milliseconds to be at, I added a multiplier here of 1,000 counts per millimeter, so that's why the number is larger. And so we just, sequence through the time from 0 to 140, and of course, as we set the frequency, we'll set it to a kilohertz, which is a 1 millisecond per count. So for every count time, every millisecond, we get a master position, and then the slave should be in the corresponding position. So this relates to time, and then this column relates to the position we want to be in. And of course, in between these points, we do a linear interpolation in the drive. So no fancy cubic spline interpolation, just pure straight linear interpolation. Position is closed every 250 microseconds, so there's some interpolation, and then we, update the position deterministically between those points. So for the configuration, I'm going to use an internal master. I mean, normally camming follows like an encoder on a conveyor or something that varies in speed, but this will be an internal master setting the clock. So once every, one count, 1,000 counts every second, or 1 count every millisecond. Okay, so of course you can change the clock rate to make it sequence through quicker. I'm just going to set the time, set the conversion, and I'm going to toggle input 2 on the edge. So when it sees it's the rising or falling edge, I think it's the rising edge, we'll see the trajectory start, and it'll start into the lookup table. It'll go there and then come back, and the profile should look like this. So I've got an input 2. It's pulled up right now. It's high. When I on the falling edge, Let's make sure it's enabled. So I'm in a disabled mode. I've got CME2 connected. I'm pushing buttons. I get disabled. Press the enable button. I would advise not setting 0 position while you're enabled because it'll jump. But you could do homing first, right? And then follow a CAM table. Okay, so you could use the CVM Indexer program to home and then use the CAM table, repeat. Of course, this is all, you don't do this if you have a CAN master or an EtherCAT master. You just do PVT in your master in the software. But this is just purely switches and hardware. We want to follow this profile. So on power up or reset, the drive will be enabled and it'll be camming, and it uses table 0 because that's what we've selected here for the various CAM tables we could load, and you can insert more points if you want. Have a bigger CAM table with various profiles, but we're keeping it simple now. Let's run the CME scope. So I'm going to look at the profile velocity, which is the position over time. You could look at the commanded and actual position, of course. I like to watch the following error. We could monitor the current to make sure we're not exceeding the current limit of the motor, and but I'm just trying to concentrate on the commanded position and the limited position. These should be on top of each other. And then there's an in motion bit because we have a tracking window. I'm trying to take it down to like, hey, tell me when I'm within, I don't know, we could do a larger number here, 5 counts, maybe 500 counts, 10,000 counts for 1 rev of this motor will get us, a millimeter. Not 1 rev, but so many counts per millimeter. I think I said 1,000 counts per millimeter. Anyways, so we can set a window, and I can monitor the in motion bit. And while the trajectory is running, it will be in motion. But when we are done with the move, it should be in the tracking window. So scope is ready to trigger. My input goes low and then goes high. The move is, oh, we got to hit record. Let's do that again. Go there and come back. And so the profile, you see there's a very similar looking image here because that's the definition of the profile. And so you can see when we started, there was some acceleration to get to that position from 0 to the new position, and then runs at a constant until it has to go from this position to the next position trajectory. And then here's the following error at less than 500 counts. And my in motion bit says I'm still executing and not done with the move until the end here. I'm actually tracking here, so that I'd have to monitor like a tracking bit or something, or at position, if I want to know when I'm at this position. And I'm actually at the position here where the following error goes to 0. There's a little bit of crossover distortion, so looks like there's a slight shift in actually getting to 0, but then it turns around and comes back the other way. So the position is the commanded and limited position. I guess we should track the actual position. Position, actual motor position. Okay. Let's hit record. Run it again. So between the commanded or limited position, we have an actual position. Yeah, there's a little bit of following error, so it lags, and then it gets in, and then it lags again. So right in here, well, it's really hard to see in counts, but we're like some counts off, 500 less than 500 counts, and then we turn around and go the other way and develop another lag in the other direction. So it's not till we turn around that we start developing the following error to 0. So maybe, maybe we could affect this by some tuning, maybe a little bit more proportional gain. Very aggressive tuning here. Reduces the following error, this little overshoot. And still a little bit of lag. So maybe I should not be so aggressive with my tuning. Oops, wrong button. Trace cancel. I disabled it. Control panel. Back to camming mode. Hit record. And make the move again. So the idea is we can affect the tuning so that our following error does not go negative if we don't want to, say, bump into something. And then we can, after the move is executed, we can pull back out again. Okay, that's basic fundamentals for camming, and we got to play with the tuning some more to zero things out, but that's just a simple matter of tuning. Thanks for watching.